This is problem 533, Smith Van Ness 8th edition. A refrigeration system cools a brine or saltwater solution from 25 degrees C to minus 15 degrees C at a rate of 20 kilograms per second. Heat is discarded to the atmosphere at a temperature of 30 degrees C. What is the power requirement if the thermodynamic efficiency of the system is 0.27 or 27%? And you're told that the specific heat of the brine is 3.5 kilojoules per kilogram degree Celsius. So I've drawn here a little schematic of this system. We've got this cooling process where the brine is coming in and leaving at 20 kilograms a second. It comes in at 298 K, it leaves at minus 15, or that's what, 283 Kelvin. Our surroundings temperature is 303 Kelvin, and the important thing that we're told is that the efficiency of this process is 27%. What are we asked to find? We are asked to find what? Find the power requirement. So power, that basically it's work divided by time. So we need to find the real work, all right? And we are given an efficiency. That probably means that we should also calculate an ideal work. And that's what this problem is testing you on. Towards the end of chapter 5, the concepts of real work and ideal work and lost work were presented. And this is what this problem is asking you about. So in almost every case, it's going to be the way we do this is we're going to calculate the ideal work, and then we'll apply the efficiency. We'll apply the efficiency where the real work we'll take the ideal work, and we got to figure out, do we multiply by the efficiency or divide by the efficiency? Well, where is the work going in this process? And I've drawn it here. But work, what is the power requirement? That means work is going into our system, right? And the reason why work has to go into our system is because we are taking something, we are removing heat, right? We are removing heat and expelling it to a higher temperature, right? If we were operating this at 0 degrees C in an environment that's 0 degrees C, we wouldn't have to worry about it. We just let it circulate at for a certain amount of time and just let the natural heat transfer take care of our temperature change. Or actually, it would have to be minus 20 or so. So it would have to be a very cold environment for us to just let natural heat transfer do this. So if we want to cool things down, we need to put work into the system. The thermodynamic efficiency of this engine, or actually we should call it a heat pump, but it's a little confusing. But think of this as kind of an engine that's transferring heat. Is 0.27, and so that's going to be the ideal work. The real work is going to be the ideal work divided by the efficiency. It is going to take more work to do this than the ideal work. So that's what we're going to have to do. So if we go to equation 520 in your book, that gives us an equation for the ideal work. The ideal work is equal to m dot mass flow rate, and this is for one stream, times delta H, right, minus T surroundings times delta S, right? So m dot is and remember these equations were derived for an open system where we have one stream entering, one stream leaving. We know what m dot is, all right? We know what T surroundings is. Do we know what delta H is? Delta H is equal to what? Delta H is our heat capacity times our temperature difference, which would be T out minus T in. Right, and our heat capacity, I'm just going to use C. In general, heat capacity of CP and CV are the same, and for liquids we generally use just C. So that is 3.5 kilojoules per kilogram degree C. Actually, we can make this degree Kelvin because this is a delta C, times T out. T out is what? 273 minus 15, 258 Kelvin minus 298 Kelvin. All right, so that's our delta H. That's going to be kilojoules per kilogram. All right, so we have that number right there. Our T surroundings, that's given to us. That's 303 Kelvin. I'm not adding the 0.15. T surroundings, so we know that. We know delta H. We know M dot. M dot is 20 kilograms per second. All right, so we know that. What about delta S? Delta S, and this is of the brine. Right, this is of the brine solution. So think about how can we calculate delta S of the brine? Well, it's obviously not an ideal gas. Another source for calculating delta S would be, do we have any property tables? And I'm sure someone somewhere probably has some property tables for different brine solutions, but we have no idea what the salt concentration is. There's just no way to figure that out. So property tables are not an option here. But remember, we can treat this as an incompressible liquid. It's an incompressible liquid, and so delta S of an incompressible liquid is equal to the heat capacity times natural log of T2 over T1, so that would be T out over T in. And so this will be 3,500 joules per kilogram degree Kelvin times natural log of, this is 258 Kelvin over 298 Kelvin. All right, and so the Kelvins cancel. We're left with joules per kilogram or kilojoules per kilogram, however you want to leave that. And delta S of our brine, that is minus 504.2, and that will be joules per kilogram Kelvin. And then we can calculate our ideal work. And we put our numbers in, and that will be 2.57 times 10 to the 5th joules per second. And that's the same thing. What's a joule per second? What? That's a watt. All right, so that's watts. And our units are we're kilojoules or joules per kilogram, kilogram per second. We're left with joules per second. So that's our ideal work. And so our real work, and notice this is positive for it going into the system, which makes sense. So our real work is equal to W ideal divided by 0.27, and that's equal to 9.52 times 10 to the 5th watts. And you can change that to kilowatts if you would like, or kilojoules per second. So that's what this problem is getting you to work on, is the concepts of real work and ideal work, and make sure if work is required, is going into the system, we divide by the thermodynamic efficiency. If work is produced, of course, then we will multiply. But we have our equation. You don't need to really derive anything over again. That's given to you in your book for one stream for the ideal work. The only thing that we needed to add to this was calculating the entropy change for an incompressible liquid, which we covered in class. Remember, that's not covered in your textbook, so see the notes for that calculation, that derivation, and then calculating the real work from that.